continuing our discussion of the geometrical properties of curves in space, now we want to discuss Frene-Serre frame or TNB frame. Now this frame is basically a set of 3 vector fields on any given curve, and this set of vector field and its derivatives gives us all the geometric information of curves in R3. Now let's see what we have achieved so far. We have defined unit tangent vector field on any unit speed curve, and using this unit tangent vector field we were able to define one geometrical aspect of any given curve in R3, which is the curvature, which is the rate of turning of any given curve. Now we want to explore more geometrical properties, and hence we are going to need more vector fields on any given curve. Now to define these vector fields, we want to impose some certain conditions on these vector fields. So first of all, we want them to be mutually orthogonal at each and every point. So this is just to optimize our calculations, and the second condition that we want is that they should be unit vector fields, so that at each and every point we have a set of 3 mutually orthogonal unit vectors. Okay, now this is a kind of the same conditions that we impose on ijk. So when we discuss vectors in R3, we have these 3 mutually orthogonal unit vectors I, j and k, and using these 3 vectors we can discuss most of the properties of vectors in R3. For example, we can add them, we can multiply them, dot product, cross product, and etc etc. We can resolve the vectors in different directions. So it's a kind of an optimal tool for discussing vectors. Okay, so we want that at each and every point on the curve we have 3 mutually orthogonal unit vectors, and these mutually orthogonal unit vectors at each and every point will provide us a kind of basic tool for determining the geometrical properties, and using these 3 vector fields is more preferred than using the usual ijk's, because the usual ijk's does not contain any geometrical information, but these vector fields do contain some information. So for example, using the rate of turning of t, we can actually calculate the curvature, but this is not possible for ijk's, because ijk's does not contain any such information, or if they contain, then it is very hard in that case to extract that information from this tool. So for example, so whenever I'm saying ijk in this case, it means that u1 and u2 and u3, and since it is a curve in R3, so at this point I can calculate. So for example, u1 a vector parallel to, let's say, x-axis, u2 a vector parallel to, let's say this is y-axis, and u3 a vector parallel to z-axis. Okay, so at each and every point we can also calculate u1, u2, u3, but this new set of vector fields that we are going to calculate, and in fact we have already calculated one vector field, which is unit tangent vector field, and we are now going to calculate the other 2. Now this set of 3 vector fields contains much more geometric information about any given curve. Now to define 2 further vector fields on any given curve, observe that we have this unit tangent vector field. Okay, now since it is unit, so we can say that the magnitude of t at each and every point is 1. And what does this imply? This implies that the square of this is going to be equal to 1, and hence t dot t is going to be equal to 1. Now we know that given any 2 vector fields, we can actually calculate the derivative of their dot product using the formula that v prime dot w plus v dot w prime is going to be equal to 0. Now using this property, this differentiation of the dot product of 2 vector fields, we can say that this t dot t is equal to 1. So differentiating both sides, okay, let me write down. So differentiating both sides of 1, so this is 1, so differentiating both sides of 1 would give me t prime dot t plus t dot t prime is going to be equal to 0. So this implies that t prime dot t is equal to 0. Now let's see what do we get. So t prime dot t is equal to 0. Now why this information is important now? Because we know that whenever the dot product of two vectors is 0, then they are orthogonal, or there is an angle of 90 degree between them. So this little information provide me a hint for defining our next vector field which is perpendicular to t. Okay, now given any curve, we can define tangent at each and every point, which gives me tangent vector field. Now at each and every point, this information tells me that at each and every point we have a vector which is perpendicular to this t vector, and it is not clear at the moment that what is the magnitude of t prime. Okay, so we have this t prime vector which is perpendicular to t. Now in order to make sure that this t prime or this vector is 1, we divide it by its magnitude just to get a unit vector in this direction. So in this way we will be able to define two vector fields on any given curve, and at any particular point these two vectors given from these two vector fields are going to be orthogonal, and these are going to be unit, and we want to impose the condition. Okay, now a vector field is called normal if v dot b prime is 0. In other words, it is perpendicular to the tangent. Okay, so v dot t is 0, and this curvature vector field is normal to b. So we have seen that this vector field t prime, as we have seen that it is perpendicular to t. Okay, so this is beta double prime, so which is another way of saying t prime. Now we have a vector field now which is perpendicular to vector field t. Now in order to make sure that it has unit magnitude, we divide it by its norm, and we know that what is norm of t prime? It is basically the curvature. So if we define this t prime vector field by its magnitude, which is the curvature, then this new vector field is known as principal normal vector field. It is perpendicular to t and it is unit. Now let's see why it is unit. Okay, now we can easily calculate the norm of n at any particular point. So this is going to be equal to norm of t prime over curvature. So this is going to be equal to norm of t prime. Okay, so norm of t prime divided by this curvature, and we know what is norm of t prime? It is curvature. So kappa over kappa is going to be equal to 1. Now there is one important condition that we impose on any given curve in order to define this principal normal vector field, and that condition is that curvature should be greater than 0. And this is not a very strong condition. So why it is not strong? Because we are just excluding only one case of curves in R3, and that is the case of straight line in R3. So by just taking curvature strictly greater than 0, we are excluding one simple case of straight lines. And these straight lines, the geometry of these straight lines is very simple, and we have also discussed about these straight lines in our elementary courses. So we are not compromising too much by taking kappa greater than 0, and hence now we have another vector field on the given curve which is perpendicular to the tangent vector field or unit tangent vector field, and it is also a unit. Now what does this principal normal vector field tells us? Now this tells us in which direction the curve is going to turn. So for example, at this point we can see that the curve is going to turn on the right side, so it will be somewhere over there, and at this point we can see that the curve is going to turn in this direction, so it will be this principal normal vector field at this particular point will be in this direction. And similarly, if the curve is like this, then it will be in this direction. So it is somehow always inside the curve. Okay, so this is the geometrical interpretation, and of course it contains some more geometrical information as well that we will extract later on. Now using these two vector fields, we can define a third vector field which is the binormal vector field, and this is pretty easy now. So because we have two unit tangent vector fields, and by taking the cross product of these vector fields, we can define another vector field which is of course perpendicular according to the definition of cross product. It is perpendicular to t and n, and it is unit as well. So combined all of these information together, we can now say that for any given unit speed curve in R3, kappa is greater than 0, so that we can define principal normal vector field. The three vector fields T and B on beta are unit vectors that are mutually orthogonal at each and every point. Okay, so we have T, we have N, we have B. Now proving that they are mutually orthogonal and unit vector fields, so it is kind of simple tasks. So it is unit speed, so that's why norm of T is equal to norm of beta prime is equal to 1, since it is unit speed. And similarly N is defined as the norm of T prime over kappa, so the norm is going to be equal to norm of T prime, as we have discussed earlier on as well. So kappa over kappa, we can divide it with kappa because kappa is greater than 0, so this is going to be equal to 1. Now what about B? So binormal vector. So remember, don't confuse between this beta and B. So this is B, which is the binormal vector field. So this is going to be equal to T cross N. And by definition of cross product, so this is going to be the fact that the angle between T and N is 90 degree. So this is going to be equal to norm of T, norm of N, and sine of the angle between them, and the sine of the angle between them is 90 degrees. So that's why the norm of T is 1, norm of N is 1. Okay, so and hence this is going to be equal to 1. And now when we say that calculating the norm or the cross product norm for any two vector fields, then it is exactly the same as we are calculating for each and every particular point. Okay, so at each and every particular point we have this T, we have this N, and at this point these are just two vectors. So let's say this is point alpha of T naught, so this is T of T naught, this is N of N T naught. So these are two particular vectors in R3 because it's a curve in R3. Okay, so let me sketch the axis. So this is a curve in R3, and at this particular point we can say that we can use our usual definition of cross product, and we can actually calculate this thing. Okay, now moving on. So we know that T dot N is equal to 0. They are mutually orthogonal. Now what about T dot B? So this is equal to T dot T cross N, which is obviously 0 because the cross product is perpendicular to both the vectors T and N. So similarly N dot B is going to be equal to N dot T cross N, which is N T cross N, which is once again going to be equal to 0. So all of these vector fields are mutually orthogonal and unit at each and every point. Now a set of three mutually orthogonal unit vectors to R3 at any given particular point is called a frame at that point. Now this information is important because now we have a frame at each and every point of a unit speed curve. So given any curve in R3 and at each particular point we have three mutually orthogonal unit vectors. So in other words, we can say that we have a frame at each and every point, and this is not just ordinary frame. So once again let me rephrase this statement. At each particular point we can actually calculate this u1 parallel to x-axis, this u2 parallel to y-axis, and this u3 parallel to z-axis. And this is not very this does not contain geometric information about any given curve, but this T, N and B that we just calculated. Okay, so this is T, this is N, and this is B. So this T, N and B, they contain much more geometrical information about any given curve. Now these unit vectors at each and every point, so they define three planes. So Tn plane is known as the osculating plane, Tb plane is called the rectifying plane, Nb plane is called the normal plane. Okay, so you can see from this animation that at any given point we have three little planes that you can see. Okay, so and you can also observe that at any given point we have three mutually orthogonal unit vectors, and these vectors are deciding these planes. Okay, so this is the first plane, the second plane, and this is the third plane. Okay, now this triplet of three vector fields on any given curve is known as the Frane-Serre frame field, or sometimes known as TNB frame field on any given curve beta. Now in this discussion we have introduced three mutually orthogonal unit vector fields on any given unit speed curve in R3. Now these three vector fields contain geometrical information about any given curve, and in the next discussion we will see how we can extract this geometrical information.